Hey guys, Ziki here. Welcome to the GMAT Pill study method. There's a ton of good stuff here today. Later in this video, we're going to cover poker probability. On the GMAT, you'll see combination and permutation questions. Knowing poker probability will solidify your understanding for the test. We've all been to the casinos, but do you really understand how all the probabilities are calculated? What's the probability of getting a pair, two pair, three of a kind, a straight, a flush, full house, four of a kind, straight flush, royal flush? How do we get this pie chart with all the answers? Well, it all comes from this table of numbers here. We're going to show you exactly how to calculate each item line by line using the NCR formula so that they add up to 100%. We'll go through questions from our practice pill platform in real time so you can see exactly how we answer these questions and eliminate answer choices in less than 1 minute. Are you ready? Let's get started. Here's a warm-up question. In a kickball competition of 9 teams, how many possible matches? Alright, so a match is between 2 teams, so that's basically out of 9, you choose 2. So that's basically 9 on top, 2, and then the 7. Now this is basically 9 times 8 times 7, and then that cancels out the 7 on the bottom. There's still a 2 factorial here, and that's 72 over 2 factorial. That's 36. Answer choice D. Now, let's say we're really bad at factorial calculations and, what's another way of doing this? This is the preferred way, method 2. Now here's method 2, and another way of doing it is out of 9, choose 1, then out of the remaining 8, choose 1. And does order matter? Well, team 1 playing team 2, it's the same as team 2 playing team 1, so order does not matter. We have to divide by 2 factorial, and it's basically 9 times 8 over 2, and that's basically 72 over 2, and that's 36. So again, this is method number 1 over here, and this is 2 over here. Either way, you get 36, answer choice D. How many ways can you pick something? Well, this question can be divided into 2 major parts. One part is when you pick something and then you can pick it again. So for example, if you think about a slot machine, right? The first slot you can pick out of so many different symbols and values. That second slot you can pick from the same number of values, and same with the third one, and so on. When you think of a password, when you create a password for a login, your first character you can choose from A to Z. That second character can also be chosen from A to Z. Now, this is called variations, right? Because each time you pick something, you can still pick it again. The other type of picking stuff is when you pick it and then you can't pick it anymore, right? So if you're choosing from a team of 10 people to be in a committee of 5, well, once you choose one of them, you can't choose that same person for that subcommittee. So that's what these combinations and permutations are. These are when you're picking something and then you don't put it back into the pot. You pick it and then you keep picking it from remaining options until you get to 0. Whereas with variations, you pick it and then you can also continually pick that event. And this is true for passwords. This is true for slot machines. So here are some examples. With variations, you use the exponent calculation. And I said before with slot machines, if you have, 3 slots and each slot has 7 possibilities, well, that's basically 7 to the 3rd power. And the same thing with passwords. If you have a password and you have to decrypt 8-letter password assuming only lowercase alphabetic letters, well, A to Z, that's 26. And since there's 8 letters, that would basically be 26 to the 8th power. And then how many ways can you roll 3 dice? Well, each dice has 6 options, so that's basically 6 to the 3rd power, because you have 3 dice. How many distinct ways can 3 guys vote for 3 girls? Well, that's basically 3 to the 3rd power. So these are examples of questions that involve using exponents to find the total number of ways you can pick or how many ways of doing something. What about combinations and permutations? This is when you use the NCR formula, right? So one example is how many ways can you pick a team of 3 out of 10, right? You're picking out of a pool of people, and when you pick that first person, you have fewer people to choose from in the remaining rounds. So this is when order does not matter. If you pick 10 people and you pick players number 1, 2, 3, then it doesn't matter if you pick 2 first, or 1 first, or 3 first. It doesn't matter. That is the same team of the same 3 people. So that's why order does not matter. And in these cases, you have to adjust for the fact that order does not matter by dividing by 3 factorial. Now, how do you word this question so order does matter? Well, that's if you had 3 starting players and each player had like a letter on his jersey, and then they all line up to form some kind of 3-letter sequence word. And how many 3-letter sequences can be created when the 3 selected players line up, right? So this is when order matters. So this is when order does not matter. This is when order does matter. What's another example? Example B, how many ways can you roll 3 identical dice and get 3 different numbers? Because you have identical dice, it doesn't matter if this particular dice has a 5 and that one has a 3 and another one has a 1. You still have that combination of 5, 3, 1. Whether it's 1, 3, 5, 5, 3, 1, 1, 5, 3, it's still the same set of 3. So order does not matter. And then when order matters, that's when how many ways can you roll 3 differently colored dice and get 3 different numbers, right? Notice I changed identical to colored, and that's basically showing that each dice is distinct. So if you have like a yellow dice and then a blue one and then a green one, those are distinctly different. So if one of them is a 1, the other one is a 5, the other one is a 3, well, if you move them around, the different colored dice can show different numbers, and so that way you're going to get more possibilities, and when you have more possibilities, that's when order matters. So this is another example. Another example, when you have 5 marbles, and you want to distribute those 5 marbles in 3 identical baskets, such that each basket has at least 1 marble, right? The other version is, well, if they had different colored marbles in distinct baskets, right? So if this is similar to B. Then you can think of another one. How many ways can you get a pocket pair in poker, right? How many ways can you get a pocket pair? Well, if you first get an ace of spade and then an ace of diamond, that's the same as if you got an ace of diamond and then an ace of spade. So that combination, that single combination of the spade and the diamond counts as the same. That's why order does not matter. Now, order matters if the question were worded like, if you are dealt a pocket pair, how many different ways could that pair have been individually dealt to you? Right? With that same example, you getting the diamond first and then the spade is different from you getting the spade and then the diamond, right? So these are different ways of wording almost the same question, but in one case, order does not matter. The other case, order matters. So why does any of this matter? Well, it matters because it affects the calculation. If you're using something like slot machines and you have to pick from the same set of values each round, then you use variations. You use the exponent. If you pick something and you choose from remaining options, then you use the NCR formula. And sometimes you're going to need to adjust for the fact that order does not matter by dividing by R factorial, and sometimes you don't, in which case that's order matters. In those cases, you can just multiply things out. And I'll show you exactly what I mean by going through each of these examples. Example A, how many ways can you pick a team of 3 out of 10 people? Versus, 3 people out of 10, how many ways can they line up together to form some 3-letter sequence? Okay, so in this case, since players numbers 1, 2, 3 is the same as 3, 2, 1, they're the same team, then order does not matter, and you simply do 10 choose 3, right? 7, 20 over 6. You calculate it in the same way. It's still 10 times 9 times 8, but you do not need to divide by 3 factorial. You do not need to divide by that 6. So it's basically just 10 times 9 times 8, and then you just leave it at 720. So the difference is, this is all the possibilities. If order does not matter, meaning if 1, 2, 3 is the same as 2, 3, 1 and 3, 1, 2 and all that stuff, then you're going to need to divide by 3 factorial, which is 3 times 2, which is 6. In this case, you don't need to divide by 3 factorial. It's simply 720. If we write it out, it's the same thing. 10 choose 1 times 9 choose 1 times 8 choose 1. The only difference is here you divide by 3 factorial. What about B? In this case, you have identical dice. Over here, you have differently colored dice. So this is when order matters, and this is when order does not matter. And when order does not matter, remember you have to divide by the number of dice you have factorial. So you can think of it like this. For the first dice, you have 6 potential values. right? So it's out of 6, choose 1. And then since they all have to be different numbers, then after that first number was chosen, you can't choose it anymore. Now out of the remaining 5, you choose another dice, another value. And you can't use that value anymore. Now out of the remaining 4, you choose another value. So you do that 3 times, and then you divide by 3 factorial. That's how you get 20. Then with permutations, when order matters, you do not need to divide by 3 factorial. The only difference is you just multiply it straight out. Out of 6, choose 1, then out of 5, choose 1, then out of 4, choose 1. It's 120. So this is the difference. When order matters with differently colored dice, you get more, you get 6 times more, and that's 120. And when you have identical dice, order does not matter, you have to divide by 3 factorial. Part C, how many ways can you distribute 5 marbles in 3 identical baskets? And in this one, it's 5 color marbles in 3 distinct baskets. So this question requires a little bit more thinking. You have to actually structure the question first before you do any calculations. If you're distributing 5 marbles in 3 identical baskets and each basket has at least 1 marble, well, there's only so many ways you can do that. So for example, one basket can have 3 and then the other 2 can have 1, or one basket has 2, another basket has 2, and that third basket has 1. So that satisfies the requirement that each basket has at least 1, right? So this is the calculation. Out of 5, you choose 3 for that first basket. Then out of the remaining 2, you choose 1 for that basket. Then out of the last one, you choose 1 for that third basket. And then since these are identical baskets, they don't really count distinctly, and so you have to account for the fact that these are duplicates by dividing by the number of baskets factorial, which in this case is 2 factorial. So this turns out to be 10. And then if you do the same thing for here, out of 5 choose 2, then out of the remaining 3 choose 2, then out of the remaining 1 choose 1, you still have to divide by 2 factorial because the 2 and the 2, these are identical baskets. So in this case you get 10 and 15, they add up to 25. Now with the permutation version, it's a little bit different. You still have the combinations of 3, 1, 1 and 2, 2, 1. The only difference is you do not need to divide by 2 factorial. And that is because each basket is distinct. And the marbles are different colors. So a yellow marble in this one is different from an orange marble in this one. So that's why you don't divide by 2 factorial. And then you also have to multiply by 3 choose 1 because you could pick whichever spot to have 3 marbles. Like this one, you know, basket number 1 could have 3, basket number 2 could have 3, or basket number 3 could have 3. So there's 3 possibilities there. That's 3 choose 1. And you do the same for the 2, 2, 1. In this case, 3 choose 2, it also equals 3. But it's basically saying, you know, you pick any of these 3 baskets to have 2 marbles each. So those 2 things are the main differences. One of them is you have to multiply by 3, and then the other one is you do not divide by 2. And so that net effect, the net effect is basically that each item here is 6 times what we had originally on the left side. So this was a 10 here. This is 6 times, which is 60. This 15 becomes a 90. And then this 25 becomes a 150. So everything here is 3 factorial times what it was here on the left. Now, pocket aces, part D. Now, how many ways can you get a pocket pair? Well, one way is to sequence it, right? So first, the method is to break it down. First, choose the first card, then choose the second card. Since order does not matter, you divide by 2 factorial. So the calculation is, you know, you have 13 values from ace to king. Out of those 13, you choose 1 to be that pair. Then you multiply by the 4 suits, right? Out of the 4 suits, you choose 1 of those suits. Then out of the remaining 3 suits that are left over, that are remaining, you choose 1 again. And then you divide that by 2 factorial because order does not matter, and you did 2 sequences here. 1 for the first card, 1 for the second card. And that gets you to 78. Another way to do this, second method, is basically just do 13 choose 1 for whatever value you want, you know, ace, 2, 3, all the way to king. And then for the 4 suits, choose 2 of them. Right? So either way, you get 78. Now, if the question were worded a little bit differently, you know, if you are dealt a pocket pair, how many different ways could that pair have been dealt to you? right? So did you get the ace of spade and then the ace of heart, or did you get the ace of heart and then the ace of spade? So the order here matters. And that's why in this case you do not divide by 2 factorial. Everything else stays the same. And in general, you're going to have 2 factorial times more than this. So whatever this is, 78, you're going to have 156. But everything else in the calculation is exactly the same. Now, dating. Now, this example doesn't work out exactly perfectly, but let's take a look. How many different ways, how many dates can happen between 3 guys and 3 girls? Well, the first guy can date 3 girls. The second guy can date 3 girls also, and then the third guy can date 3 girls. So the answer is 9. That's basically out of 3 choose 1, plus out of 3 choose 1, plus out of 3 choose 1. So that's 9. How many different ways can 3 guys and 3 girls pair up for a group date? Well, if you fix the first guy and you say the first guy has 3 girls to choose from, right? So out of those 3 girls, choose 1, right? So then the second guy has out of 2 girls, right? There's 2 remaining girls, you choose 1. Then the third guy says, well, out of that last one you choose 1. So it's basically 3 choose 1 times 2 choose 1 times 1 choose 1, which is 6. Here the order matters because of calculation, because you're fixing the first guy, then the second guy, then the third guy. So since order matters, you do not divide by 2 factorial. So again, this is a chart breaking down all the different kind of problems you can have. Some of them involve using exponents for calculations. Some of them involve using the NCR formula. And then within the ones using NCR formula, sometimes you're going to need to divide by R factorial, sometimes you won't. You divide by R factorial when order does not matter. Here are examples of questions that involve order does not matter, and that's when you divide by R factorial, and then sometimes order matters, in which case the calculation is actually easier. You just don't divide by R factorial. So now that you understand when to use exponents in your calculations and when to use NCR formula in your calculations, let's go ahead and do some GMAT problems. Given that there are 5 basketball players per team, how many ways can you select 2 players from 3 teams? Alright, so there's 3 teams, A, B, and C. Each one has 5. So you can imagine, a group of 5 people on each team. You have to choose 2 players, and those 2 players can come from one of these 3 teams, or 2 of these 3 teams, and there's no single team that gets chosen twice. So you can't choose 2 players from the same team. Okay, so basically, out of these 3 possibilities, you have to choose 2 of them. So out of 3, you choose 2, and then for each of those selections, you have 5 people to choose from. You choose 1 of them, but since you're choosing 2 players, you do that twice. So that's how you set it up. 3 choose 2 times 5 choose 1 squared. 3 choose 2, this is basically just like this. Then this one is 5 factorial over 4 factorial and 1 factorial. The 4's cancel out, so you're left with 5 here. Here you're left with 3, and so this is basically 3 times 5 squared equals 75. So that's answer choice D. So in terms of concepts, it's all about setting up the question correctly. If you have 3 teams here, always think about how many are you choosing out of, all right? So there's 3 possibilities. You're going to choose 2 of them. So that's automatically 3 choose 2. Then you think about, okay, well, for each situation that you choose, let's say you choose A and C. Well, for A, you have 5 players to choose from. And then for C, you have 5 players to choose from. So that happens for every possibility. And that's why you do 3 choose 2 times. Out of 5, you choose 1, and you do it twice. So you square it. That's the same as multiplying it again by 5 choose 1. So in terms of calculations, you should know that, x choose y, 3 choose 2, that's the same as 3 factorial on the top, 2 factorial on the bottom, and then whatever it takes to add up so that the bottom adds up to the top, and that's just 1 factorial. So anything, for example, if you had 7 choose 3, that would be 7 factorial over 3 factorial, and then you add a 4 there. So the simple thing about these things is 5 choose 1. Anytime you have a number where the difference between these guys is just 1, or is either the maximum or the minimum. So 3 choose 2 or 3 choose 1, they both equal just 3. When you have a bigger number like this, and this number here is either a 1 or a 4, then you know the answer is just 5. And the reason that happens is because if this were a 1, you have the 1 factorial here, but then you have to also add in that 4 there. And this 4 factorial cancels out the 4 factorial up on top, and so you're only left with the 5 on top. So if you get used to seeing these kind of things, then it's easy to do the math. So if I'm used to seeing this stuff, I would say, oh, 3 choose 2. Oh, this is very close to 3. I know this is just 3. So 3. 5 choose 1, that's the same as 5 choose 4, and they're both just 1 away from 5, so I know the answer is just 5. So then 3 times 5, and then you square the 5. 5 squared is 25 times 3, that's 75. So as a recap, we were given a word problem with a hypothetical situation and asked about possibilities. We have 3 teams, A, B, and C. Each team has 5 players. Our job is to choose 1 player from 2 of the 3 teams. So out of the 3 teams, you choose 2, and then out of those 5 players for each team, you choose 1, and you do that twice for each of the 2 players. And that's how you set up this formula. Do the simple math and identify that whenever the number is just 1 away from the first number, then you know the answer is just the first number. So then it's just 3 times 5, and of course you have to remember to square it, and that gets us to 75. Here's a more complicated question. I'll answer it first, then we'll talk about it. A team of 6 cooks is chosen from 8 men and 5 women. The team must have at least 2 men and at least 3 women. How many teams can be created? Okay, so at least 2 men, right? So if you have 2 men and the 6 cooks, there must be 4 females. You can also have 3 men. If you have 3 men, then the other 3 must be female, and that satisfies at least 3 women. 4 men. Well, if you have 4 men, then the other 2 have to be female, but that violates at least 3 women, so this is no good. So these are the only 2 options that we can play with. So let's do men first. Out of 8 men, alright, so out of 8 men, choose 1 of them, then out of the remaining 7, choose 1. And that's for men. And this is men. And then for women, this is women, out of 5, you choose 1. Right? So you have 4 women to choose from. So out of 5, you choose 1. Then out of the remaining 4, you choose 1. Then out of the remaining 3, you choose 1. Out of the remaining 2, you choose 1. So that way you have 2 men and 4 women. Now, does order matter? Well, between the men, it doesn't really matter, and between the women, it doesn't really matter. And so this, you have to divide by 2 factorial. This, you have to divide by 4 factorial. Now again, this is for 2 men and 4 females, in which case you have 56 over 2. And then you have here, these cancel out, right? 4 factorial cancels out, so you basically have 5 here. So that's basically 28 times 5, and that's equal to 140. So that's 2 men and 4 females. What about 3 men and 3 females? Well, that's 8 out of 1. Out of 8 men, choose 1. Then out of 7, remaining 7, choose 1. Then out of the remaining 6, choose 1. And this you divide by 3 factorial. And that's for men. For women, you have out of 5, you choose 1. Out of 4, you choose 1. And then out of the remaining 3, you choose 1 for that last 6 cook. And this also divides by 3 factorial. We know 3 factorial is 3 times 2. That cancels out with the 6. So that's basically 56 times, here we have 5 times 4, which is 20. 20 times 3 is 60. And then that's 60. You have to divide that by 3 factorial, which is 6. And so that's basically 56 times 10. And that's 5 560. So the total ways is equal to this 140 here plus the 560. 140 plus 560, and that's equal to 700. That's answer choice D. So D, 700, is our final answer. So what's going on here? We're asked to pick 6 cooks, and then for these 6 cooks you have a pool of people. Out of the 8 men, you have to choose 2 men, and then out of the 5 women, you have to choose 4 females, right? So, but before we did that, the only ways to get 6 cooks satisfying these requirements is to have 2 men, 4 females, or 3 men and 3 females. There's no other way. You know, having 4 males and 2 females doesn't make the cut. So there's only 2 possible combinations to make it work. And then within this combination, 2 men and 4 females, then you have to figure, well, you're picking out of the 8 men twice, and out of the 5 women, you have to pick 4 times. That's for this part. Then we have to do for the second part, out of the 8 men, you choose 3 times, and then out of the 5 women, you choose 3 times. So those 2 combined will get you the final answer. Now, the method here I show you is basically the GMAT pill preferred method. You do it sequentially. You pretend first out of 8, you choose 1, then out of the remaining 7, you choose 1. And then if order does not matter, which it does not matter in this case, then you adjust for the fact that it does not matter by dividing by 2 factorial, basically the number of sequences you have. And you did that for men, but you also have to do that for women. For women, you're choosing out of 5, and you're doing that 4 times. 1, 2, 3, 4. And then you have to divide by 4 factorial. Now, this is a method that doesn't make you have to do a lot of calculations and cancellations. And you can simply do 8 times 7 and then divide it by 2. Other methods, I'll show you in a minute, involve a lot more factorial calculations and cancellations. And if you're not very good at keeping track of the calculations, it's very easy to mess up. So the way we prefer here is to do it this way, where you first structure it. Then when you structure it, then you do each calculation sequentially, and if order does not matter, then you divide by that factorial. So this is the way we like it here. So another way to do this is basically out of 8 men choose 2, and then out of 5 women choose 4, right? So that's basically this first part. And then you add that to out of 8 men you choose 3 this time, and then out of 5 women you choose 3 this time. So this calculation is easy to set up. If you're good at the calculations, this could work out as well, like this. 5 choose 1 you know is basically this over 4 and 1. Then this is basically 8, the 3 and 5, and then this is 5, 3, and 2. So this is basically 8 times 7, the 6 cancels out, divided by 2 factorial. This is basically just 5. This is 8 times 7 times 6, and then this is basically just 3 factorial on the bottom, which is basically 6. This cancels out. You have 5 times 4, the 3 factorial cancels out. This 2 is here. So then you have 28 times 5 plus this 56 times 20 over 2 is 10. So then you get 140 plus 560, and that's equal to 700. So either way, you still get answer choice D for 700. This one requires you to do a lot more writing out numbers and canceling things out. It was easier to set up here, but anytime you do a lot of something, choose a number that's other than 1 or itself, then the calculations can get a little bit more messy and there's more chances for error. So for those of you who want to have fewer calculations, the method we showed you before is actually more efficient. So as a recap, we saw this question as a probability combinatorics question that has requirements, and it can't be done straight up calculating it. You have to actually structure it first. And when you structure it, you have 2 men and 4 females, or 3 men and 3 females. Any other option does not work. And so based on this information, we have to pick 2 men, then pick 4 females. Well, out of how many are we picking? Well, we're picking out of 8, you pick 2, right? So that's how we came up with 8, choose 2. Then out of 5, choose 4. We realized that in order to avoid the other calculations, one better method is basically thinking of it sequentially. So basically out of 8, you choose 1, then out of 7, you choose 1. You do that twice. Order does not matter. You divide by 2 factorial. Then for the 5 women, out of 5, you choose 1. Then out of 4, you choose 1. Out of 3, you choose 1. Out of 2, you choose 1. And you do this for 4 women. All right, so this basically, anything choose 1 is itself. So you know 8 times 7 over 2, that's 56 over 2. That's basically 28, right? So 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. 120 divided by 4 factorial, which is basically 4 times 3 is 12. 12 times 2 is 24. So this is basically 28 times 5, and that's equal to 140. So this was 2 men and 4 females. We then did the same thing for 3 men and 3 females and came up with 560, right? So 560, you add these 2 together and you get 700, and that's how we got answer choice D, 700. Peter took a 52 card deck and he removed everything until there's only 10 jack, queen, and ace, and then hearts and diamonds. All right, so there's 5 number or face cards, and then there's 2 suit variations. So the way to find what's the probability that he deals himself at least 1 pair of cards. So the key word is at least. Then you do 1 minus the probability of no pair. All right, what's 1 minus the probability of no pair? That's basically 1 minus. Now intuitively, there's only one way to get no pair, and that's when you get 1 of each of these cards, and that would simply just be 1. But for those of you who don't understand the intuition off the bat, you can do it mathematically and say, well, out of the 5 cards, first you choose 1 of them, then you have from the remaining 4 you choose 1, then from the remaining 3 you choose 1, and so on. And you have to divide by 5 factorial to account for the fact that order does not matter. You have to multiply this by, out of the 2 suits, you choose 1 suit for that, and you do it for each of the 5 cards. So you raise it to the 5th power, and all of this, all of this here is divided by, out of 10 cards, you choose 5. So really, this big expression is what we're solving for. And I already said intuitively that this part here is actually equal to just 1. And intuitively, that's basically when you have 1 of 10, 1 jack, 1 queen, 1 king, 1 ace. That's one possibility, and that's the only possibility where you do not get any pairs. And for each of these 5 cards, you have to pick, a suit. And so this one variation leads to, this one possibility leads to multiple variations because of the suits. You could have 10 hearts, jack hearts, queen hearts, and then king diamonds, ace diamonds. All those possibilities are accounted for with this expression 2c to the times 1 to the 5th power. So let's do the math. 2c1 is simply 2 and to the 5th power, that's 32. And then you divide that by 10, and then 5, and 5. So this is all 1 minus. So that equals 1 minus, 32 over 10 times 9 times 8 times 7 times 6 over 5 times 4 times 3 times 2. This 2 and 3 cancels with the 6. This 5 gets rid of the 10. You get 2 left. 4 and 8 gets you 2 left. This 2 and this 2 combine to make 4, and that 4 cancels out with the 32 8 times. So that gets rid of this. So you're left with 1 minus 8 over 9 times 7. And that turns out to be 63 on the bottom. 63 minus 8, and that gets you to 55 over 63 as your final answer, and that's answer choice C. So in terms of concepts, this is a poker question where you're left with only 5 number of face cards and 2 suit variations. In order to find the probability that at least, that he gets at least 1 pair of cards, you have to do 1 minus the probability that he gets no pairs. And he gets no pairs when he gets exactly 1 unique card from each of the 10 Jack, Queen, King, and Ace. And you could think of this as all this stuff, or you could think of it as just simply out of the 5 cards, you're choosing, each one uniquely 5 times. And so that's one possibility. So there's one possibility here times the suit variations, which is 2 choose 1 to the 5th power, because you have to do, out of the 2 suits, you choose one of them, you do it 5 times for each of the 5 cards. You divide that by the total number of possibilities, which is out of the 10 cards, you choose, 5 cards, right? So 10 choose 5. So this entire thing, you do 1 minus that entire thing. So once you plug in all the numbers, you cancel out as much as you can, do the math, it turns out you'll get 55 out of 63, and that's answer choice C. As a recap, this is a probability question that involves at least. Whenever you see at least, you have to do 1 minus the opposite. In this case, the opposite of getting 1 pair of cards, or anything higher, is getting no pairs. And it turns out intuitively, there's only one way to get no pairs, and that's getting 1 of each of these guys. If you couldn't find it intuitively, then write it out. 5 choose 1 times 4 choose 1 times 3 choose 1. That's basically out of the 5 cards, you choose the first one. Then out of the remaining 4 cards, you choose another 1 card. Then out of the remaining 3 cards, you choose 1 card. You have to divide all that divided by 5 factorial to account for the fact that, there may be duplicates, and because order does not matter. So when you do this simplifies to 1. Then you combine it with all this other 1 minus the suit variations here and the total possibilities here. Do all the math, and you'll get 55 out of 63. Now, before we get into calculating the probability of pocket pairs and pocket aces, let's first talk about the distinction between probability and number of ways. For the most part, we've been calculating today the number of ways of doing something. Now, probability is simply dividing that number of ways by the total possibilities, right? So if you're going to use this approach to calculate probability for all these poker calculations, keep in mind that you should be using, when calculating number of ways, you should be calculating it with order matters. That again is the right side of what we were talking about before, the permutations. You want to calculate and display the total number of ways you can get that particular combination. So then divide that by the total possibilities of everything. So again, probability is just dividing the total number of ways of getting a pocket pair, of getting a pocket ace, divided by the total possibilities. So out of 52 cards, you choose 2 of them, right, for your first 2 cards. So that's the total possibilities. Then on top, you divide it with the total number of ways of getting that pocket pair. Alright, so let's get started and apply this formula in the process. So probability of pocket pair. Well, in both cases, when you're playing poker, you're going to have one value, ace to king, ace 2, 3, 4, all the way to 10 and then on to king. So that's the value we're talking about. Then you're going to have the suit variation. For each of these values, you're going to have spade, diamonds, hearts, and clubs. So that's 4 variations. So you're going to have 13 possible values and 4 suit variations. And for all pockets, your first 2 cards, you're going to divide it by 52, choose 2, which is basically the total possibilities of what you can get when you have 2 cards dealt from a deck of 52. And in this case, out of 13 values, you choose 1, right? Because you have pocket pair, you don't know if it's an ace or a 5 or 7. Out of 13, you choose 1, and for that value, you have to choose out of 4 possible suits, you pick 2 of those suits. So in this case, let's say you chose ace, then you chose out of the 4 suits, you chose spade and heart. So that's 4 out of 4, choose 2. And we divide it by 52, choose 2. Now, with pocket aces, there's only one value, right, that satisfies this requirement, and that is that you get the ace, right? You can't have 2 all the way to king. It has to be ace. So there's only one way to do that. That's why here the value would just simply be 1, choose 1, and we don't write it here. But then the suit variation is the same as it is over here. So as you can see, this right side is 13 times less than this side. This side is 13 times more than the right side, right? So the only difference is that 13 choose 1 here, and if you do the calculations, this turns out to be a 0.45%. 4 choose 2 turns out to be 6, and you're choosing out of 1326 possibilities, and that's 0.45% for pocket ace. Pocket pair would be 13 times this amount, which turns out to be 78 over 1326, and that's 5.88%. Now here's an alternative method, right? So first, for pocket pair, you're doing this calculation, right? So your first card, you can pick any card out of that 52 deck, right? That 52 card deck. So any card. So out of 52, you can pick any 52. So 52 over 52 times, and then once you pick that card, now you know that the next card has to be, in the entire deck, there's only 3 other cards that match what your first card is. So first, it doesn't matter what your first card is. Then your second card has to match that first card, and there's only 3 ways to do that. And the deck reduced from 52 to 51. So then you simply just do 52 over 52, which is 1, times 3 over 51. Now, of course, you can just multiply it out. Of course, you already know the answer is 3 over 51. And this is the same as 1 over 17. And you'll get that same percentage that you got before, which is 5.88%. And with pocket aces, well, that first card you choose, you can't just choose any card. You have to choose one of the aces. So that one of the aces, there's only 4 cards in that 52 card deck that are aces. Then once you pick that one, there's going to be 3 remaining. And then the deck reduces from 52 to 51. So if you multiply the sequence, you get this calculation, and it's the same result. You're still going to get 5.88% for the pocket pair and 0.45% for the pocket ace. So this again was an alternative method of doing the same calculation we did before. Now, given pocket aces, what is the probability that you get a 3 of a kind? Now this is Texas Hold'em poker. When you have a pocket aces and then 3 cards come out on the flop. The flop again is just 3 cards that come out that are public onto the table that everybody sees. You know you have pocket aces, and the question is, what's the probability of getting a 3 of a kind? Well, you can get a 3 of a kind by having a third ace, and that's over here, probability of getting a third ace. Or there's a possibility that all 3 of these cards are the same value, in which case this would be a 3 of a kind here. Effectively, that 3 of a kind would get you to a full house overall, but the question is asking what's the probability of getting a 3 of a kind. So these are the 2 possibilities. So let's break that down. The top part, this top part deals with the third ace. This bottom part deals with the 3 of a kind. So let's look at the top part first. So this first card, out of the remaining 2 aces, you already took 2 of them, so there's 2 remaining of them. Then you pick one of them, right? So that's the first card. The second card is, you want a card that's different from ace. There are 13 total values, but now there's 12 remaining ones. Ace is no good, so there's 12 remaining ones. And out of those 12, you want to pick 2 values, right? You can't pick 1, because if you picked 1, then these would be a pair in itself. So these 2 have to be different cards. So whatever value you pick for the second and third one, for each of those 2 picked values, you have to pick out of the 4 available suits, you have to pick one of those suits. And you do this for each of these 2 cards. So these 3 are for the third ace. If you get 3 of a kind just on the flop, that would be where, for all 3 cards, out of the remaining 12 values, you pick one of them. And then for that one value, you pick 3 suits. And you do that for each value. So for each value, out of the remaining 4 out of the available 4 suits, you pick 3 of them. So in terms of calculations, this becomes 2, choose 1. This is 12, choose 2. This one is 4, choose 1, squared. You do that for this card and then for this card. And then this would be, well, out of 12, choose 1 for the value. And then for each of these things, you multiply 4, choose 3. So out of those 4 available suits, you pick 3 of them. So let's combine them all, right? So these 3, these are the calculations, right? These are the values that we care about. You combine them, and then you add this part up, right? So this part was the ace, the third ace. This part was the 3 of a kind on the flop. And the calculation turns out to be 2 times 66 times 4 squared is 16. And this all combines down to 11.02%. So again, if you have pocket aces, the probability of getting 3 of a kind, whether you get a third ace or whether there's 3 of a kind that just pops up on the flop, that's 11.02%. Now, let's say you don't have a pocket pair. If you don't have a pocket pair, what's probability of getting exactly 1 pair by the time the last 5th card comes out? So in Texas Hold'em Poker, you're given a flop on the board, so 3 cards. Then the 4th card comes out, and that's the turn. Then the 5th card comes out, that's the river. Now, if you don't have a pocket pair, how do you know by the time you play everything out, what's the probability of getting exactly 1 pair? Well, basically, you would have to have the first card for each of the 2 cards you have. You want to investigate the possibilities that that card turns out to be the pair. So for each of these 2 cards that you have, out of the 3 remaining suits for each of them, pick 1. So that would be one of the cards. Then you would have to consider the possibility that, you know, all these other 4 cards are just random values. You could pick any 4 values. And they can't be the same, otherwise that would become a pair. So you only want 1 pair, and it has to pair with what you have in your hand. Or it can pair on the board later. But we'll take into account that in just a second. For each of these 4 values, you have to pick, well, for these 4 picked values, out of the 4 suits that are available, you got to pick 1 of them. And you do this 4 times for each of the 4 cards. And before we talked about, well, you know, if you don't have a pocket pair, well, perhaps somewhere in these 5 cards there's a pair. So we have to consider that possibility. So it's basically this top part plus this bottom part. This bottom part is basically, well, you know, 2 of them could be a pair, and then the 3 of them, the 3 are remaining values. Those are chosen out of the 10 remaining. The pair would have to be out of the remaining 11, right? So you have 2 cards in your hand. They're different. So originally there were 13 possible values. You have 2 of them, so there's 11 out there remaining. So out of those 11, you have to choose 1 value to be that pair, and then you have to pick 2 suits for them. Then out of the remaining 10, you have to pick 3 suits for them, for the 3rd, 4th, and 5th card. So in terms of calculations, this becomes 2 times 3 choose 1. This is 11 choose 4. This is 4 choose 1 to the 4th power. And then this is, again, 11 out of 11 choose 1 and do it for 2 suits. Then out of the remaining 10, choose 3 cards. And for each of these 3 cards, choose a suit for them and do it 3 times. So combine all of these things together into a calculation, and you basically have this times this plus this. So this is when one of the cards matches one of your pocket pairs. So one of the cards on the table matches one of the cards that you're holding, and then this is when you have a pair on the table. You add those together, you divide it by 50, choose 5, right? Because you have 2 cards, so there's 50 cards that you don't know about. Of those 50, you have to choose 5 cards to be on the table. And that calculation, if you add it up, turns out to be 47.84685%. So there's almost a 50-50 chance that by the time you play it all out, you're going to have at least a pair, or exactly a pair in this case. The probability of getting something is obviously more than that, because you could potentially have 2 pairs, 3 pairs, or 3 of a kind, full house, anything like that. But this is the probability of getting exactly 1 pair by the time you play the flop, turn, and the river. Let's summarize our findings. So this table gives us the probability of a poker hand. And you can see that these percentages add up to 100%. And this 100% is really the 52 choose 5. And we know the total number of hands is going to be 2598960. And if you sum up this, these are all the possible hands you can get. The total will add up to 100%. So anytime you play poker, half the time you get nothing special. 42% of the time you might get a pair, 2 pair. And if you look at this, this is about, 42.2 plus 4.7. That's going to be about 47%. Then add in this, that's like 49%. And then you have 1% split up among all of these guys. So the next time you play poker and you get 1 pair, don't be too excited because it happens actually over 40% of the time. But the chance to get 2 pair drops tremendously down from 42% down to just 4.8%. And keep in mind, these are basically the probability that you get these things on a first hand. So the game of poker, sometimes in Texas Hold'em, you might get 2 cards and then you match them with 3 others. We're not talking about the probability that you get 2 pair after switching and matching other cards. We're talking about getting 5 cards. What is the probability that those 5 cards that you get without doing any switching is a 2 pair or a 3 of a kind? What is the probability that we get 1 pair, 2 pair, 3 of a kind, and a straight? And to do this, we're really going to find the total number of ways that you get 1 pair and then divide it by the total number of poker hands possible, which is basically out of 52 cards total, we choose 5. So all of these, we want to find the number of ways to get 1 pair, then divide by 52 choose 5 to get the percentage for the probability that you get 1 pair, 2 pair, 3 of a kind, and then a straight. So what is the probability that you get 1 pair? Well, it's going to be these expressions here all divided by 52 choose 5 at the end. But here the solution, we just show the numerator. So for the first card, what's the probability you get 1 pair? Well, 1 pair is basically this right here. Out of 13 cards, you want to choose which card you are having as the value. So this is the value. Out of 13 cards, choose that one value. So ace to king, which value do you want to make a pair? And then whatever value that is, let's say a 7, an 8, or an ace, you want 2 of those cards. And basically those 2 cards have 2 different variations. So out of 4 suits, choose 2 of the suits for that individual card. So once you've done that, you've already chosen that 1 pair, which is basically 2 cards, and then you have 3 remaining cards to choose from. 12 choose 3 says out of the remaining 12 cards, once that 1 value is taken out, choose any 3 unique values. Unique values such that we don't get a second pair, they are all different cards. Then for each of those unique cards, we want to choose the different suit variations for it. So the first card can have 4 suit variations, the second card can have 4 suit variations, and the third can have 4 suit variations. So these 2 together will find the number of ways that we can vary those 3 other cards. And likewise, we do the same thought process for 2 pair. 2 pair basically says, okay, well, let's choose which 2 cards we want to make pair of, make the pair of the first one, make the pair of the second, and then of the remaining last card, which there's only 1 card, there's only 11 values to choose from, and then 4 suit variations for that. Similarly, for 3 of a kind, choose which value do you want to make a triplet, and then actually make it a triplet. Out of the 4 suits, you have 3 different suits to choose from. Then, of the 2 remaining cards, you choose them among 2 cards, and then vary them. And lastly, the straight, there are 10 possible straight starting values. They can start from ace 2, 3, 4, 5, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7. And the last one is 10, Jack, Queen, King, Ace. You cannot have a straight beginning with a Jack, Queen, King. Those are not possible. So there's only 10 ways to start a straight. And then there's different suit variations for each card. And there's 5 cards, so basically just times 4 to the 5th. So that's a summary of the solution for these 4 questions. Now we have our next set of probability variations for advanced poker. Probability for flush, full house, 4 of a kind, straight flush, royal flush, and then probability that you get nothing special. So let's take a quick glance at the answers. A flush is basically saying we get 5 cards and they all have the same suit. So it might have spade, 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 and all of the cards are different. So to calculate that, we want to choose out of 4 suits, pick one specific suit that we care about, and then pick 5 unique combination cards off of that suit. Then for full house, we want to permutate between 2 cards. Basically, the first set of cards has 3 cards to it. The second card has 2 cards to it. So the permutation matters here because we might have 7, 7, 7, and then Jack, Jack, and that's going to be different from Jack, 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 and then 7, 7. Because in one case, there's 3 of the 7s and only 2 of the Jacks. In the other case, there's 3 of the Jacks and 2 of the 7s. So the permutation is going to be important for a full house, and we'll see how that's different from the calculation we did before for 2 pairs. Probability of 4 of a kind, basically choose one value that we want 4 times, then actually find all 4 variations of it. And then that last card, it could be anything. Straight flush, there's 10 ways to have a straight, but for the flush, we care about those 10. Each set has the same set of suits, and there's 4 suits to choose from, so that's 10 times 4. Royal flush specifically is 10, Jack, Queen, King, Ace, and they all have the same suit. And there's only one way to have 10, Jack, Queen, King, Ace, and then for each of that one way, we can have all of them to be spades, all of them to be clubs, hearts, and diamonds. So probability of royal flush, there's only 4 ways possible to do that. Then the number of ways to get nothing special is basically taking everything, 13, choose 5, all of the 5 unique cards out of the 13. Since we know that we cannot choose any of the same card, they all have to be unique in order to have something that's worthless. Then we want to take 10 away from that, and the 10 represents the number of ways to get a straight. So when we pick out of the 13 unique sets, or 13 cards, we take a unique set of 5. That unique set of 5 could potentially be a straight. It could be a 2, 3, 4, 5, 6. And it could be a 6, 7, 8, 9, 10. And whatever variations we get for 13, choose 5, we want to take away all the ways that we get a straight, which is 10. Because then, instead of having nothing special, we actually do have something special. So we want all the cards to be different, but take away all the ones where it could potentially be a straight. And then in the second side, we want to multiply by 4 to the 5th to represent that each card can have a different suit variation. The only cases where we want to take out is basically where all of them have the same suit. So let's say, for example, you get numbers 2, 4, 6, 8, 10. And there's nothing special in that set, but if all of them are diamonds, then you actually have a stronger hand. You have something that's called a flush. So in those cases, we want to take away the special case where you can get a flush, and that's 4 ways. You can get 5 cards, all of them spades, all of them clubs, all of them hearts, all of them diamonds. So suit variation wise, we want to take 4 to the 5th and then subtract 4 for the
to times when all of them are the same suit. So this expression gets us the number of ways that we get nothing special. And again, to get probability, you take all of the number of ways and you divide it by 52, choose 5.
What you saw today was only a tiny portion of what GMAT Pill is all about. If you like what you saw today, then you're gonna love what's inside. Remember, the GMAT is all about how you think. It's not about how fancy your prep program is. When it's just you in front of that computer taking the GMAT, it's all about how you think. And that's what the GMAT Pill is all about. We're known for our verbal products, everything covering sentence correction, reading comprehension, and critical reasoning, all focused on how to think efficiently. We've also got a solid quant program, as you can see from today. Want that GMAT score? We're here to help. Sign up for GMAT Pill.